we're going to start our first lesson on probability. This is your recorded lesson, so it's a good chance to prepare yourself for the live lessons this week. We're going to be looking at how do we calculate probabilities of simple events, so just one event at a time, and look at what relative frequency is and how you can calculate it from repeated experiments. By the end of this lesson, you will be able to go and complete clips 351 and 356 on Hegarty Maths. Remember to write up all these new methods and steps neatly in your maths book or on paper, because you will need to come back to them, and there are lots more recorded lessons that you can watch on Teams, or we watch live lessons if you want to go back over what we've been doing. So let's get started. Let's have a look at this problem. A fair dice is rolled. Work out the probability of getting 6. Give your answer in its simplest form. So this is a nice simple probability problem that you probably already know how to answer, but I'm going to show you how we're going to set this up so that when we come to more complex problems, they don't seem hard at all. So there are two words that you need to know really well in probability, and you need to be able to make the distinction between them. The first one is an event, and the second one is an outcome. So in this case, the event that's going on is I am rolling a dice. Okay. And if my event is rolling a dice, that means my outcomes are all the possible things I could get when I roll a dice. So hopefully you can see quite clearly your outcomes. You could roll a 1, you could roll a 2, a 3, a 4, a 5, or a 6. So they're all your possible outcomes. And then once you know what your outcomes are, you can then calculate the associated probabilities. So we can then say, right, well, I'm going to find out what is the probability of getting a 1, what's the probability of getting a 2, all the way up to 6. Now in this question, they've told us I've got a fair dice, and that word fair is really important. It means that all those outcomes are equally likely. So when you see the word fair, it's telling you you've got equally likely outcomes. There is no one outcome that is more likely than the other. So equally likely, so that means if all my outcomes must equal 1, so all the probability of all those outcomes must equal 1, I've got to share that 1 equally between 6 possible outcomes. So each of these probabilities would be a 6th. If I'm looking at the actual question they're asking me, they're saying work out the probability of getting a 6. So I'm looking at this one. What is the probability of getting a 6? Well, the probability of getting a 6 is equal to 1 over 6. And there's your answer. Okay, so I know the way we set that might be a bit longer than what we're used to, but if you understand and thoroughly grasp what's going on here, when we come to the more complicated problems, you're going to fly through it. So let's have a look at the next question. It says a fair dice is rolled. So we've got that word fair again. So I'm automatically thinking equally likely outcomes. I don't know what's happened there. Let's move that out of the way. Or are you thinking equally likely outcomes? Work out the probability of getting a number less than 2. Give your answer in its simplest form. So we set out exactly the same again. You could just write E here if you wanted, the event. Well, we are still rolling a dice. And if you wanted to, you could write rolling a fair dice to remind you you're rolling a fair dice. What are your possible outcomes then? Well, I could get a 1, a 2, a 3, a 4, a 5, or a 6. And again, because it's fair, they're equally likely. So my probabilities, well, all my probabilities are going to equal 1, and they are spread nice and equally, a 6th, a 6th, a 6th, a 6th, a 6th, and a 6th. So what I mean by the probabilities equaling 1 is if I added these all together, I should get the answer of 1, because definitely one of these things is going to happen. There's no other number that I could get when I roll this dice. There is no possible way of this dice landing on a corner. It will be one of these numbers, so it must equal 1. So this time it says work out the probability of getting a number less than 2. So I look at these numbers less than 2, and again, you've only got one possible outcome here. If it's less than 2, it must be a 1. So there's only one thing circled. So I say, okay, the probability of less than 2 is equal to 1 over 6. Same as before, there's your final answer. Okay, so that's the basics of how we set these problems. Let's begin to look at how this might build in challenge. So your turn here. A fair dice is rolled. Work out the probability of getting a factor of 2. Give your answer in its simplest form. So for this question, I'd like you to do 3 things for me. I would like you to tell me what is the event, what are the possible outcomes? And I'd like you to try and give me the probabilities. Okay, and once you've done that, I want you to press play and let's check our answer. So pause now. Okay, welcome back. Well, let's just check we set it up nice and clearly. The event, you are still rolling a fair die. A fair dice. Okay, so that means your outcomes are you could get a 1, a 2, a 3, a 4, a 5, or a 6. The probability will always add up to 1. And because you've got a fair dice, here, fair dice, that 1 is being equally spread across 6 possible options. So I've got a 6, a 6, a 6, a 6, a 6, and a 6. This time, I now want to have a look at what the actual criteria is. So it says the probability of getting a factor of 2. So again, I'm going to set you 2 things to do now. I would like you to list me the factors of 2, like we've done when we've done factorising, like we've done when we've done surd. So list me the factors of 2, and then I want you to circle any outcomes on this list that are a factor of 2. So pause now. Okay, welcome back. So the first thing I asked you to do was to list me the factors of 2. So I was going to list the factors of 2. I do it like this. Factors of 2 are 1 and 2 and 2. Oh, I've written 3 there. 2 I can stop straight away because 2 is already on my list. So I don't need to go any further. So they're the only factors of 2, 1 and 2. 2 is an exceptionally special number. It's an even prime number, the only even prime number that exists in this world. So the factors of 2 are 1 and 2, which means that I go to my table, and it means I could have this outcome and I could have this outcome. So here's something new. You've now got a situation where you could pick either of those 2 outcomes. So you've got 2 potential outcomes that would meet your criteria. This one and this one. Okay, when you've got 2 potential outcomes that meet your criteria, to finish that question off, you add the probabilities together. Because what we're saying is the probability of getting a factor of 2 is equal to the probability of getting a 1 on the dice or a 2 on the dice. So those 2 things mean exactly the same. Saying what's the probability of getting a factor of 2 is the same as asking the question, what's the probability of rolling a 1 or rolling a 2? And suddenly now, what we should see is that is 2 possible outcomes you could get that would meet the criteria. So the probability should increase, it should get bigger, because you could either get a 1 or you get a 2, and both those things would be okay. So that's why we add. So we say, okay, that is 1 over 6, add 1 over 6. And again, the great thing about this dice being fair is we've got the same denominator on the bottom. So I can add these fractions, and when we add fractions, you check the denominator is the same on the bottom. If it is, you keep it the same in your answer, and you just add the top. So our final answer is 2 over 6. And if I simplified it, I could divide top and bottom by 2, and I would get 1 over 3 as my answer. So the add-on there is when you have multiple outcomes, we add. Multiple outcomes, we add them together. So let's begin to have a look at some different types of questions. We're going to move away from dice. So here, a single card is drawn from a standard 52 card deck. Work out the probability of choosing a heart. Give your answer in its simplest form. So again, we're going to set it up like this. We've got an event, we've got outcomes, and we've got the probability. Okay, so our event is we're picking a card from a 52 card deck. So that 52 card deck is a normal deck of cards. The possible outcomes you can get when you pick from a set of cards, well, there are many different outcomes you get. We could literally list every single one. You get 1 heart, 2 heart, a 3 heart, a 4 heart, a 5 heart, a 6 heart, a 7 heart, an 8 heart, a 9 heart, a 10 heart, Jack of hearts, Queen of hearts, King of hearts, and Ace of hearts. And you would get that for all the hearts, for all the clubs, for all the spades, and all the diamonds. So you could write that out, and it'd be a huge list, and it'd waste you a lot of time. So this is where you need to think a bit cleverly about, well, what do I actually care about? Well, in this question, I'm caring about picking a heart. So the fact whether it's got a 1 on it, a 2 on it, a 3 on it, does not bother me. I only care about the fact that it's a heart. So one of the outcomes must be a heart. So what else could you get other than a heart? Well, you could get a diamond. You could get a spade. Or you could get a club. So actually, even though that there are 52 times 4 different possibilities of cards, what you care about is the fact that, you care about the fact that there are a heart, a diamond, a spade, or a club. And again, what you need to know about a deck of cards, which they might not tell you in the exam, is in a 52 card deck, that is split evenly or split fairly between clubs, diamonds, spades, and hearts. So this is split fairly. So you know the probability will always equal 1, even if it isn't fairly. And then in this case, that 1 is split between 4. So this becomes 1 over 4, 1 over 4, 1 over 4, and the clubs is 1 over 4. So each of these is split fairly, which means each of these represent a quarter. So if I want the probability of hearts, well, there's only that one that meets that criteria. So final answer, the probability of hearts equals 1 out of 4, and you're done. Okay, let's have a look at another card question. So you have a go at this one. It says a single card is drawn from a standard 52 card deck. Work out the probability of choosing a king. Give your answer in its simplest form. So 3 things I'd like you to start off with. I would like you to give me the event. I would like you to list all the possible outcomes. Now there will be a fair few possible outcomes here, so you do a bit of space, and then have a think about what that means the probabilities will be. So pause now and press P when you're ready to have a go at going through it. Okay, welcome back. So a single card is drawn from a standard 52 card deck. So that's your event. You are picking a card from a deck of cards. Okay. Your possible outcomes. Well, this time you don't really care about clubs, spades, hearts, diamonds. You care about the value on the card. So your outcomes, and there are a few here, are going to be you could get a 1, a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, and then you get a jack, queen, king, and don't forget the ace. So there are all your possible outcomes. So here you've actually got 10, 14 different outcomes. Okay, now we know that all of these probabilities are going to add up to 1, and also we know that this is going to be fairly done. Okay, there is the same number of 1s in a deck of cards as there are 7s, as there are jacks, as there are kings. So all of these will be a 14th. So you've got a 14th, a 14th for 2, a 14th for 3, a 14th for 4, a 14th for 5, a 14th for 6, a 14th for 7, a 14th for 8, a 14th for 9, and so on. And what do we care about? Well, we care about choosing a king, so a 14th for king. And you've got your answer. Okay? Now, let's have a look at the next problem. So, Gavin and Mark have played 28 tennis matches. Gavin has won 17 times. Mark won the rest. Estimate the probability that Gavin wins and estimate the probability that Mark wins. So this seems like a very similar question. The only new words in this question are the words estimate. And you're being asked to work out an estimate for what a probability is. And the reason you're estimating is because now we don't know for a fact what the chances of Gavin and Mark winning if they played all their matches. The only thing we have to go on is, and this is kind of where it links, we have an experiment. The experiment is they've played 28 times so far, and from that experiment, Gavin has won 17 times. So in our experiment, we can make estimations, just like in science. When you do an experiment, you can make hypotheses and you can make predictions but you might not know fully 100% that that's true. That's why the question says estimate, and it means you have to use the data from your experiment to work it out. Everything else stays the same. So here, my event would be, Gavin and Mark have played 28 tennis matches. Gavin has won 17 times, Mark won the rest. Estimate the probability that Gavin wins. Well, the event is Gavin and Mark play tennis match. Gavin and Mark play a tennis match. Okay, and your possible outcomes, well, there are only two possible outcomes. You could have Gavin win, or you could have Mark win. Okay, in tennis you can't draw the match. So you could have Gavin win, or you could have Mark win. Now, we now need to do our final step, which is the probability. So in this question, we haven't been given the probability. We know it's definitely going to add up to 1, but we are going to have to use our experiment data to find out what these two things are. Well, in my experiment, Gavin won 17 times. So I'd say 17 out of a possible 28 times Gavin won. And if I wanted to find out how many Mark won, I would say, well, there are 28 times altogether, and the number of times that Gavin didn't win would represent the number of times that Mark won. So 28 minus 17. So we get here 11 out of 28. So that's how many times Mark wins. So for part A, if I have estimate the probability that Gavin wins, I'd have the probability that Gavin wins, I'm going to put G wins, is 17 over 28. And I don't know it for 100% sure, but using my experiment, I would say 17 over 28. And the probability that Mark wins would be the remaining 11 over 28. So that's how I'd calculate those two. Now, time for you to have a go. So it says a biased dice is rolled 100 times. The results are shown in the table. So this is no longer a probability table. This is telling you that if I rolled this dice 100 times, I got the number 1 12 times. I got the number 2 29 times. I got the number 3 26 times. I got the number 4 9 times. I got the number 5 14 times, and I got the number 6 10 times. It says the results are shown in the table below, so that's how the table works. Estimate the probability of rolling a 6. So remember, think to yourself, well, why is it asking me to estimate? It's asking me to estimate because I'm using this experiment to work out my probabilities. So exactly the same again, I'm going to have my event, my outcome, and my probabilities. So in this case, my event is rolling a dice. I don't know if it's fair, it doesn't tell me, but my event is rolling a dice. My possible outcome, let's give myself some space. Yeah, there we go. Our possible outcomes, well, because it's a dice, are a 1, a 2, a 3, a 4, a 5, and a 6. And now work out my probabilities. Now, we could work out each individual one. So I could say, right, 1 would be 12 times in my experiment, I got a 1 out of 100. For the 2, I got it 29 times out of a possible 100. For the 3, it was 26 times out of a possible 100. For the 4, it was 9 times out of a possible 100. And for the 5, 14 times over a possible 100. And the 6 was 10 times over a possible 100. And that probability will always add up to 1. But in this question, to be fair, the only thing I actually cared about was the outcome of 6. So you didn't need to do this stuff here if you didn't want to. You could have gone straight to 6 and just taken the information from the table. So the probability, or the estimate of the probability of rolling a 6 was 10 over 100. In its simplest form, well, I could divide by 10 and divide by 10, 1 over 10. So immediately you'll begin to think this isn't a fair dice, because if it was a fair dice, that number there should be 1 over 6, and it's not, it's 1 over 10. Okay, so let's have a go at you having a turn. We've got this one. It says a biased dice is rolled 100 times. The results are shown in the table below. Estimate the probability of rolling a multiple of 2. A multiple of 2. So again, I want you to have a look at this one. Remember, it says estimate because we are using the data from the experiment. Okay, we're using the data from the experiment. So let's have your event, your outcome, and the probabilities. Okay, so pause the video now and fill that in for me, and then press play when you're ready to check that information. Okay, welcome back. So your event, well, the event is, again, you are rolling, and they've told you it's a biased dice. So biased means it's not equally spread across the different outcomes. One outcome is going to be more likely. So your outcomes are 1, 2, 3, 4, 5, 6. And the associated probabilities, well, you've done it 100 times, so this would be 29 over 100, 16 over 100, 19 over 100, 10 over 100, 13 over 100, and 13 over 100. And we care about rolling a multiple of 2. So rolling a multiple of 2. So to start with, just like we did in the previous question, I'd like you to list all the multiples of 2. So up to, once you've gone past 6, you can obviously stop. So list the multiples of 2. And then I'd like you to circle all of those ones that are on this list. Circle all of those ones that are on the list. So pause now. Okay, welcome back. So multiples of 2. Well, if you're a multiple of 2, it means you're in the 2 times table. So a multiple of 2 will be 1 times 2, which is 2. 2 times 2, 4. 3 times 2, 6. 4 times 2, 8. Now I could go on, but there's no point, because from there, there's no way of getting any of those, because those numbers are bigger than 6. So the only outcomes I'm interested in are the 2, the 4, and the 6. So this guy, and this guy. So this is another example of where I've got multiple outcomes that meet my criteria. So the probability of rolling a multiple of 2 is exactly the same as asking for, well, what's the probability of rolling a 2, a 4, or a 6? So now, instead of just picking one outcome, you could pick 3, which means we're going to expect our probability to get bigger. So we're going to say, right, if I was calculating this, the probability of a multiple of 2, okay, and just think to yourself, can you remember what you need to do? We add all the various probabilities. So I've got 16 over 100 plus 10 over 100 plus 13 over 100. So it's equal across 100, which is nice. So I've got the same denominator, 1, 2, 3. That's good. That means I have the same denominator in my answer. And my job now is to do 16 plus 10, which is 26, plus 13, which is 39. So final answer, 39 over 100. Okay, one more. It says, Ian and Sarah are testing whether a coin is biased or not. The results are shown below in the table. Work out Iman's experimental probability and Sarah's experimental probability. So both of them have done the same experiment. They flipped the same coin. One of them has flipped it more times than the other. So if we look at this table, this is again representing my experiment. And again, hopefully what you can see here is in this experiment, Iman has flipped it 50 times and got 21 heads. And Sarah has flipped it 800 times. So she's flipped it a lot more than what Iman has. She flipped it 800 times. And the number of heads she got was 395. So if they ever ask you, if you want to have a think about, well, whose data is more accurate? Whose data should I trust more? We're always going to trust Sarah, because she did the experiment more times. She's got more evidence to base her answers on. Now, Iman's experimental probability is exactly how we've been doing it before. We would say, okay, for Iman, what's my event? Flipping a coin. What are the possible outcomes? Heads, tails. Probability? Well, it's going to have to equal 1. And for Iman, number of heads is 21 over 50. So the number of tails you must have got, well, if you've got 21 heads, that would mean you've got 29 tails. So it's 21 out of 50 and 29 over 50. Now we can do exactly the same for Sarah. So for Sarah, we would say exactly the same. Your event is flipping a coin. Your outcome is heads and tails. And let's move it down a bit. For Sarah, your probabilities are for heads 395 over 800, and for tails, well, how many would you have left from 800 if 395 of them were heads? You would have 405 over 800 with tails, because both those probabilities must add up to 1. There's no other option that you could get. So this represents Eman's experimental probability, and this represents Sarah's experimental probability, because you're using the experiment, just like it says in the first part of the question, to generate what your probabilities are. Okay. Last question I want us to look at today, and this one comes up in your Hegarty, so it's really worth understanding it. It says, Glenn rolls a biased dice 400 times. The results are shown below in the table. Jake rolls the same dice 720 times. Estimate how many 5s he can expect to get. So you're now using your experimental probability to calculate a probability, and then to calculate how many times you're going to get 5. So we set up the problem exactly the same, never changes no matter how hard or how easy the question is. We say, okay, what is the event? What are the outcomes? So here the event is rolling a biased dice. So it's biased, which means that one outcome is more likely than the other. So rolling a biased dice. Your outcomes then could be 1, 2, 3, 4, 5, and 6. And if we were going to work out your probabilities using the experiment here, so here's my experiment, I could have 95 out of a possible 400. I could have 134 out of a possible 400. There were 45 times that she got a 3 out of a possible 400. There were 26 times she got a 4 out of a possible 400. There were 75 times she got a 5 out of a possible 400. And finally, there were 25 times she got a 6 out of a possible 400. Now, which out of this list do I care about? Well, I'm looking at trying to find how many 5s I could get. So I'm picking this box here because I want to know what's the probability of getting a 5. So I now know what the probability of getting a 5 is. So I can say, okay, the probability, or an estimate for the probability of getting a 5 is equal to 75 over 400. So that's the probability. If I roll the dice one more time, what are the chances on that one more time that I roll it, I get a 5, and it's 75 out of 400. But Jake rolls it not once, he rolls it 720 times. So out of those 720 times, we want to know how many times are going to be 5. So you take your probability for rolling it once, and you times it by 720, because we're basically saying there are 720 opportunities that you get a 5. So on our calculator, we do 75 over 400 times 720. And that gives us 135. So again, if I broke that up, here is the probability, and there is the number of times that you're going to roll the dice. So in total, out of the 720 times, I'm going to expect 135 times I will roll a 5. Okay, so that's how we finish those questions off if they ask us to actually work out or apply that probability information. So that's the recorded lesson for today. Hopefully it's taken you through some of the basics of how we work out simple probabilities. And again, I'll reiterate, you might be able to do some of those simple probabilities in your head, and that's absolutely fine, but you need to know the importance of setting up the problem, events, outcomes, probabilities, for when we come on to what we're doing the rest of the week. Tree diagrams are much harder questions, so make sure you have a really good practice of it. And the best way you can have a practice of it is to get onto Hegarty clips 351, 356.